Hello everyone, welcome to SJC Contents. This is Dr.L.Jethruth Emelda Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore. I am going to deliver a lecture on First MSc Mathematics, Graph Theory and its Applications, subject code EPMT14. In this part, we are going to discuss about Hamiltonian graph, which is called as the dual concept of the Eulerian graph. First, we shall see what is Hamiltonian or Hamiltonian path, and then we define Hamiltonian cycle and so on. Definition: the Hamiltonian path of a graph G is a spanning path of G. That is, if a path contains all vertices of the graph, then it is called spanning path or Hamiltonian path. The next definition is Hamiltonian cycle. A Hamiltonian cycle of G is a cycle which contains all the vertices of G. Then Hamiltonian graph. If G contains Hamiltonian cycle, then the graph G is said to be Hamiltonian graph. A graph G do not contain Hamiltonian cycle is called non-Hamiltonian graph. Now we shall see some examples. So this in this graph, you are not able to find a Hamiltonian cycle. So though it is connected but no cycle exists, therefore it is known as non-Hamiltonian graph. Here another graph. This graph has Hamiltonian path, contains all 5 vertices, but it has no cycle. So it is also known as non-Hamiltonian graph. So in this graph, you can find a path called Hamiltonian path, and also it contains Hamiltonian cycle. Therefore, this is an example for Hamiltonian graph. The next is K6 graph, namely we call it as a complete graph on 6 vertices, which contains Hamiltonian cycle, and so it is called Hamiltonian graph. So this is a Peterson graph. It is a non-Hamiltonian graph because the removal of any vertex from G yields Hamiltonian graph, and so we call it as a Peterson graph is also a hypo-Hamiltonian graph. So this is called a theta graph. It is not hypo-Hamiltonian graph. Note, every Hamiltonian graph contains Hamiltonian path. A graph containing all Hamiltonian paths need not contain a Hamiltonian cycle. The graph having Hamiltonian path need not be Hamiltonian. For example, the theta graph has Hamiltonian path, but it does not contain Hamiltonian cycle, hence it is not Hamiltonian graph. Now we move on to maximal non-Hamiltonian graph. We have a definition. A maximal non-Hamiltonian graph G is non-Hamiltonian such that by adding a single edge between any two non-adjacent vertices of G forms a Hamiltonian graph. Now we have an example. The first example says it is non-Hamiltonian graph. By adding single edge to this graph will yield a Hamiltonian graph. The next is an example. In this graph also this form Hamiltonian path, so it is not non-Hamiltonian graph. Now we move on to the necessary condition for a graph to be Hamiltonian. The statement is, if G is Hamiltonian, then for every non-empty proper subset S of V such that the number of component of G minus S is less than modulus of S. So this is a statement of necessary condition for a graph to be Hamiltonian. If you want to prove that a graph, every graph is Hamiltonian, then this following condition must be satisfied, that is number of omega of G minus S. Omega of G minus S stands for number of component of G minus S, which is less than or equal to modulus of S, where S is nothing but non-empty proper subset of a vertex set V. So here we see the proof now. Given G is a Hamiltonian graph, since G is Hamiltonian, by the definition of Hamiltonian graph, we can say G has Hamiltonian cycle Cn. If G has Hamiltonian cycle Cn, then we can call it as a spanning cycle, that Cn is taken as spanning cycle. If Cn is a spanning cycle, then we can call it as that is a spanning subgraph of G. Okay, then I'll define a vertex set V is vertex set of G and S is a proper subset of V of G. Now, by removal of vertices of S from C, C stands for cycle, we get the graph G is disconnected. Okay, the resultant graph is disconnected. So the number of component of G is increased now, but the number of component is less than or equal to number of number of vertices in S. Therefore, we shall write the number of component, that is omega of G minus S, is strictly less than mod S. We take this as equation 1. Now, since C minus S is a subgraph of G minus S, and hence omega of G minus S is strictly less than omega of C minus S. So we take this as equation 2. From equations 1 and 2, we conclude that omega of G minus S is less than mod S. Since G minus S more edges than C minus S, then we get the result. Okay, after completing this proof, we shall have a result. The result says, if S is a non-empty proper subset of V such that omega of G minus S is strictly greater than modulus of S. Modulus of S is nothing but the cardinality of S, or you can say that the number of vertices in the set S. If so, then G is non-Hamiltonian. So to prove this result, we shall have the following theorem. Suppose G is a theta graph, and let us define S is equal to V1 and V3. The graph G minus S is disconnected graph with 3 components, V2, V4, V5. S is I am taken as the collection of vertices V1 and V3. If I remove that vertex from the graph G, then the resultant graph become disconnected. So it has 3 components, singleton V2, V4 and V5. Hence, the number of component of G minus S, namely omega of G minus S, equal to 3, and the number of vertices in the set S is 2. So this satisfies the requirement of the result, namely omega of G minus S is greater than modulus of S. So here, therefore, we can call it as that G is a non-Hamiltonian graph. Hence, theta graph is non-Hamiltonian. So this is a graph I have taken. This is called theta graph. In this theta graph, we have V1, V2, V3, V4, 5 and V5, 5 vertices. So here I have taken S is equal to V1 and V3, collection of vertices V1 and V3. If I remove that vertex S from the vertex set V minus S gives V2, V4, V5. Then definitely if I remove this vertex V1 and V3 from the graph G, the resultant graph is disconnected. We'll be getting G minus S is equal to V4, V5, V2. Okay, so these are 3 components. Namely, we call it as a totally disconnected graph. Therefore, the omega of G minus S is 3 and modulus of S is 2, which satisfies the condition of the result that omega of G minus S is strictly greater than modulus F, which implies G is non-Hamiltonian. So thank you for patience listening.